Okay, in the previous sections, in the integrations, definitions, definite integral, I hope if I were giving you the graph with some exact positions, and if I say that can you compute this with left endpoints, right endpoints, I hope you can visualize how the rectangle should be. For example, let me draw in the book. For example, if I have this, we have like this. This is like a random, but you know this point here, and I think you can take for example, this position here, and then this position here. This will be the right endpoints, right? Okay. And same thing when you did the left endpoints. Let me draw it different colors. Start from here and this part, right? And this part, the red one here. This will be the left endpoint. And how about the midpoint? The midpoint, it means that you will have the point that is on the curve is its middle point. So perhaps the positions will be maybe this point here, like that, maybe here. Okay, and then you can set the delta with, and n is the rectangles number, how many rectangles we have. Okay. And sometimes the calculation is simple, so it doesn't really have like a lot of decimals. If we have a lot of decimals, well, perhaps it shouldn't be as complicated as it seems. Okay. Usually, if you are given a graph like that, usually the numbers that is matching the rectangle, the numbers will be easy to follow. Just notes for the I think the definite integral. Okay, so we start today with the indefinite integral. Okay, and I think more review will be coming maybe tomorrow. Okay, so we are going to review most integral, especially the indefinite integral and the substitutions method. Okay, consider when we have integrations from a to b of f of x dx, if the capital F is the antiderivative, then this will be equal to these equations, right? Where f is antiderivative of f. Okay. So if we have the just the integrations of f of x dx without any initial point or the end points, we call these terms as the indefinite integral. While this part here, this is definite integral. Because it has definite exact point, okay, and exact area. So this means this integration fx dx is equal to the antiderivative of x, and it means that if we derive the antiderivative, it will be convert to the original equations. But for example, to give you an illustration, if we just integrate the x squared dx, we know that the antiderivative of the x squared will be 1 over 3 x cubed. And don't forget that we are always having something to add. Okay. It's a c, it's a constant. Okay. Because we know that when we derive a constant, this is due to when we derive a constant, this will be 0, c is constant. Right? So we need to add c because we are not sure whether it is going to be just that equation or having a number to add or maybe nothing at all. But for sure, we just add plus constant. Okay, the difference between the definite integral and indefinite integral, as you may see, the definite integral, okay, this is supposed to be a, b. The definite integral is a number, okay, it's a number, while the indefinite integral is a function. But of course, these two, the definite integral and the indefinite integral, we can connect those two. So we can connect them, we connect those two, that if we have integration from a to b of f of x dx, you could imagine the indefinite integral, compute that, and then plug in the endpoints. I think some of you already learned this a little bit, right? So this is how we connect the indefinite integral with the definite integral. In the beginning, we define the definite integral as the summation of the rectangle, right? Or something like rectangle. And then in indefinite integral, we know that this is basically given by the fundamental theorem of calculus, that this is, we call the antiderivative, right? So it's actually the antiderivative, and then you need to plug in b and a, and it's becoming the, we can write this as the beginning, we can write this fb minus fa. And the constant here, it seems is a number, like a simple number, but actually in our course, in our section here, the constant will be really important, especially because some integrations, we have like a really complicated functions that you need to integrate. Sometimes it has several solutions. It has several solutions. Those several solutions can be understood by the difference of the constant. If we disregard this constant, then we will confuse on some integration that might have different solutions. So you need to don't forget to plus c every time you have the indefinite. Okay? And then some of the basic for indefinite integral is this part. Okay. This is the most common, and I think if you know the derivative, I think you can look from the right to see when you derive this, when you put this, when you derive this, and this. I think if you already know the derivative, you should be also not very familiar with this. So I hope it works like that. Like this, the tangent inverse. Whenever you see any 1 over x squared plus 1, when you integrate, this is going to be tangent inverse x. And this cosecant and cosecant cotangent, not really that important, as long as you know the sine and cosine. Yeah, I think that will be the key. And also for 1 over x, don't forget your ln have the absolute value. Because when we derive this, it can be 1 over x, it can be negative 1 over x. When we try to compute, the derivative is the same if we have ln x. 1 over x, the other one is also the same graph. Right? So don't forget the absolute value to make sure that it's positive. Oh yeah, I forgot that this is called the net change theorem, this part. This is the net change theorem. And the derivative integrations also relate to physical problems like the velocity, distance traveled. If we have some curve that is going to be represent the velocity over time. So velocity is the curve, and you have the axis. The x-axis is time. Then the area under the curve is the displacement or distance. You can say both of them. Or okay, I'll tell you how we can see in some problems after this page to see how we understand the situation within the integral. So let me go through the new page. So let me introduce you to, let's say, object moves along, let's say, a straight line. With position function st. Then its velocity is phi t equal s prime t, right? I think it's similar to physics, kinematics, right? So when we try to integrate the phi t with respect to dt, let's say from t1 to t2, we are going to have the s t2 minus s t1. This is according to what we have in the previous page, the net change theorem, right? So we have this called the net change. Well, in our case here, because it's a position, we call this a net change of position. Or we call them displacement. Okay. But if we think, but how about the distance the object travels? So we know this is displacement, okay? But we are not sure whether all this component will be like, for example, in our curve, the area can be positive, can be negative, right? So it can be like the movement can be going forward, backward, we are not sure. But if we were talking about the distance, then all needs to be positive. Okay, you get my point? Because we need to calculate how far he walks. Okay, get my point? Okay. So we are going to have the velocity need to be positive. So, or maybe let me write in more convincing way. We need to compute the speed, not velocity. That's different thing, right? The speed. Speed is absolute value of phi t. Okay. So therefore, the integrations will be. Then we call this total distance traveled. If we have a curve like this, this is just a illustration. So this is PP. So your area will have A1, A2, and A2. A2 is under the x-axis, which if we calculate, it will be negative, right? So if you just want to check the displacement, you could take this A1 minus A2 plus A3. But if we are going to know how the distance traveled, how far he walks. Then we need to compute A1 plus A2 plus A3. Okay, I hope you get the idea. Okay, you can think like if we are taking the walks, okay, if we think the displacement, then if I walk there, maybe this is plus. If I walk here, I will be minus because I will going back to the original points, right? Because it's just a straight line. So displacement this is for distance. So displacement is just Vt. So A1 minus A2 plus A3. And distance so A1 plus A2 plus A3. Okay. Okay, since this is having an absolute value, then we are going to consider V can be a positive, V can be a negative. So we need to find those intervals. So we could take this, consider when Vt is positive, and also when Vt is negative. A simple example that can be shown here is maybe this one. Example from your textbook. So you have a particle moves along the line, and the velocity functions is t squared minus t minus 6. You have a unit meters per second in our question here. Is finding the displacement. You have the interval 1 to 4, and find the distance during the same interval. So you need to integrate this. So first you need to integrate. So for A, we are going to integrate this, or let me write this, that this is supposed to be equal to S4 minus S1, right? And we can integrate this using the antiderivative. T cubed over 3 minus 1 t squared over 2 minus 60. And then we need to plug in 1 and 4. You plug in 4 inside, and then plug in 1 and then subtract both of them. Or we could take this, (64 over 3) minus 16 over 2 minus 24 minus 1 over 3 minus 1 over 2 minus 6. Okay, when you compute this, you know that the result will be negative 9/2. It means that if the particle moves positive to the right, then the negative will be meaning it's going to the left. Okay. So particle moves to the left. Okay, 4.5 meter. Okay. And then if we are going to take the distance, so this is displacement. So distance, note that the phi t is t squared minus t minus 6. Okay. Remember, when you have this parabolic, you will have some roots. So we can rewrite this in terms of factors. So we have t equal 3 and t equal negative 2. If we can imagine that the velocity is the first derivative of the s prime t, then if you remember the extreme theorem to find the local max and local mean, then we could also do the same thing here. This will be negative. This will be negative, negative, positive, and between negative 2 and 3 is a negative, and greater than 3 is positive. If we take t equal 1, we can check. T equal 1 is going to be negative 2. It's going to be negative, right? Going to be negative. If we have 3, it should be 0. So if we have something close to 3, let's say 2.5, it's supposed also negative. Okay, because we want the t is from 1 to 4, right? As the interval here. So we could check each one, the t4. T4 is supposed to be positive. So if we have 1 here, and 4 is around, maybe 1 is here. So 1 to 3, it's supposed to be negative, right? So it's supposed to be negative. And 3 to 4, maybe 4 is here. This is going to be positive, right? So the integrations that we can make is, we can separate these integrations. So we have the absolute value of t, dt, right? So we can separate 1 to 3. That is the negative, right? 1 to 3 is negative, so we are going to have negative phi in the equations. So we could have negative phi and plus 3, 4. That is 50. And then solve this part. So we will have negative t squared plus t plus 6 dt plus 3, 4, and then t squared minus t minus 6 of dt. Okay, you can check, compute by yourself. This will turns out to be 61/6 meter, which means that the object will walk or moves this distance. Okay? So it's going to move forward, backwards, at this distance. While the displacement is just the result at the end result. So after he moves, and then he places his positions somewhere at the negative 9/2. But this 61/6 is the total how long he walks or how far he walks. Okay. Okay, any questions? Okay. And it is also similar principle with the physics that you're, I think, already in kinematics. Okay. Some students smiling when I say physics. Okay, now let's move on to the next section, which is the substitutions method. Before I'm going into the descriptions, what substitution means, let's consider, let's say we have a function, let's say tangent, function tangent, and then x with power of 4. Okay. I hope you still remember how to take derivative. Okay. What will be the derivative? Yes, second squared, x to the power of 4. And don't forget, derive the inside chain rule, becomes 4x cubed. Okay. So we have secant squared x with power of 4, and then multiply with 4x cubed. Now, if we describe this result with the process of chain rule, if you remember chain rule, we are going to maybe take some dummy variable in between this x, okay, to help us derive, right? So let's call let x with power of 4 equal to some u, okay. And if we derive this du dx, this will be 4x cubed. So that means that if we have f of x, like for example, this is g and h, this is going to be g prime h of x, h prime x, right? So when we have this, then the f prime x, or if we take the u, then the f, just the f is tangent u. Okay, if we let the x with power of 4 equal to u. So the f prime is secant squared u multiplied with du dx. Okay? So we take this ddx like that. So then we have f prime of x is, we change back to the original equation, which is u is x with power of 4, and du dx is 4x cubed. Okay, the same process with just like the direct process, but I'm introducing you to this variable in between, which is u, okay? W variable. Now in integral, it works the same, but reverse. Okay. So if I take integrations of 4x cubed secant squared x with power of 4 dx. Okay. So let's try now to integrate this whole equation. So 4x cubed secant squared with inside function x with power of 4 dx. So if you look from this part here, what we have done in the derivatives, the best way we have to take this derivative goes back to the original equation, is taking the x to the power of 4. So the same thing when we did from the from this part, going back to the original equation, which is our question here, we are taking this x to the power of 4 as our substitution. So let's substitute this x to the power of 4. Okay. So let the u is x power of 4, and then du dx is 4x cubed, which means that the dx is 1 over 4x cubed multiplied by du. Right? Okay. So by doing so, if we implement this dx inside here, we get 1 over 4x cubed du. 4x cubed will be cancelled with this, and all the integrations become in u. And so we change x to u. So we can write down that the integrations, let me write completely, secant squared, this become u, and then dx become 1 over 4x cubed du. So this will be cancelling. So now we have integrations of secant squared u du. And what we know from the table before, the secant squared is, or you can think what kind of function when you derive it becomes secant squared. It's a tangent, right? So this will be tangent. We can substitute back again x with power of 4 and then plus constant. Okay. So that's the basic idea, okay, on the substitution techniques. So this is substitution method. So within chapter 5, we are going to more in depth with the substitution method. This is actually the last part on chapter 5. In chapter 6, we are going to apply the integrations to first to find the area between the curves and to find the volume. So what is the volume in integral? The volume is when you have a curve and you want to rotate to the x-axis or rotate to the y-axis. When you rotate that, you will see some three-dimensional shape. Okay? Well, mostly they will be like like a face or like flower face. Yeah, something like that, the shape. And in chapter 7, we are going to take more integration techniques. There are a lot, but not worthy to memorize all the names as long as you know how to do it. But the important one is from this one is substitution, and the chapter 7 is the integration by parts. I will let you know later how to do all the techniques in a quick way. Okay, let's try another example. Okay. I will give you some example first and then going to the what is actually substitution method. Okay, let's try integrations of x over square root of 1 plus x squared dx. As I will show you 3 ways to see our integration, and 3 ways to get our result. At least we have three ways. You can try just use your any methods is okay. You can use the substitutions. You can let some u to change the variable x, or maybe some functions inside. Another way to help you quickly think on how to substitute is, you see the top equation is just x. Here you have square root 1 plus x squared. Well, if you ignore the square root, if you ignore this line here, you have 1 plus x squared. If you derive, it will be 2x. Which you can think that 2x can be cancelled with this, right? So that's one way. One way to think. Okay? One way to think. And mostly that is how substitution works. Okay? If you have a fractions, or maybe you have like equations, and you think that, okay, maybe if I change some part of the functions with u, and when we derive, and then we take some time to rewrite the equation, we can cancel. That's one way for substitution. Okay? Then we have a break, and I will continue later. Okay, let's continue. I will show you some parts of how we can solve this integrations. Okay. First, and I believe most of you did this, and I think it's okay, it's correct. So first, you can substitute the 1 plus x squared. So we can have 2x dx, okay, and then we have dx is 1 over 2x du, and we can substitute, and we have 1 over 2x. Let me write like this. And this will be square root of u. And this will be du. So we can cancel all this. And we can move the 1 over 2 outside. So we have integrations of 1 over square root of u. Or we could write u with power of negative 1 over 2 du. Okay. To integrate this, I think it's easy. Just apply the power rule for integrations. So we have so we have 1 over 2, and apply this this is supposed to be plus 1, and 1 over negative half plus 1, so we have 2, sorry, it's not clear here. So this is supposed to be negative 1 over 2 plus 1. Okay. And this will be half multiplied by 2. And then this will be u with power of half. Okay, so we take that, and this equal to square root of 1 plus x squared, and don't forget the plus c. Okay, this is the first way to look at. Okay, the second perspective that I want to share with you, the same integrations. So we can take u, we can take all the square root. But instead, using this u to differentiate, we square both of them. Okay. And then take the derivative. So this will be 2u, it's du dx, but we will move the dx going to the right. Or maybe let me write this is du dx and equal to 2x. So dx is u over x du. And then this part becomes integrations of dx is u over x. So this will be x over u multiplied with u over x du, which means this is just integration of du, which means we have u plus some constant, or u is actually square root of 1 plus x squared plus c. Okay, so the substitution, it doesn't mean to be just like not necessarily like u is some part of the equation and then you derive and then you substitute. You can also take this and maybe take the squared. You can take some algebra operation before you really substitute. So you can take this, the u is the square root itself, but then you remove the square root by squaring these two sides, and then differentiate both sides and taking the substitutions back to the original equations, and you will see that it's just integration of du, which is just u, and we change back again to square root of 1 plus x squared plus c. Usually I will add the constant at the very end, the final conclusions, okay, to help us focus on solving the process, solving the middle process. Okay, the third perspective that we can apply to this integrations is we can take the integrations by taking the guess. Okay. We can also do that, and it's possible. Well, at least in my class, it's possible. I'm not sure with other professors. Maybe they don't agree with me. But at least, if we know of functions, then when we derive the result having a square root in the denominator, well, we can think the square root of x. If we derive it, will be 1 over 2 square root of x. Okay. So let's try to imagine what we have in, if we have let a function be, let's just say same function like this. but because it's simple functions, the answer got to be and it's perfectly the answer itself. So we know that the integrations will be square root of 1 plus x squared plus c. This is by considering that d dx of square root of x is 1 over 2 square root of x. For some parts in integration, the advanced guessing method will be helpful. It will be helpful. If we have time, I can give you more examples on that. But maybe one more to see how we can apply this method. If we have integrations, okay, x e with power of negative x squared dx. Okay. Again, if you use substitutions, I think it's best to give this x squared a chance, because if we take this x squared, when we derive it will be 2x. So 2x can be cancelled with x, right? But what I want to emphasize here, the last part here, is the advanced guessing. When we have e, we have some part here with x squared, but whenever we have some exponential function, when we derive, the e is still there, right? E to the x, it becomes e to the x. E to the 2x, it becomes 2e with power of 2x. Okay? Now, if we have this, perhaps we can try just e with power of negative x squared. So let's isolate that and try to derive first to see how it forms, how it performs. Okay. So try to take the e with power of negative x squared. If we take this derivative, we will see that it's going to be, let's write this part here, and the chain rule will be negative 2x. Okay. Now, if we see the result with our original question, the difference is just a constant, negative 2. So we could just try to take negative 1 over 2, multiply with this, and plus constant. So that's how also we can see this perspective. Okay? So we can say that this will be, and then plus constant. Okay. Or if you maybe want to confirm, then you could try the substitution. So you can try substitutions with negative x squared, and then you can have du is negative 2x dx, and dx is negative 1 over 2x, and you see that there will be e to the u, so it's e to the u, but we have this multiplication, so negative 1 over 2x, x will cancel, and the result is the same. Okay, the result is the same. So we are getting the x multiplied with negative 1 over 2x and multiply with e to the u du. So this will be negative 1 over 2. E to the u is e to the negative x squared plus a constant. Okay, more examples on this substitution. I think we can go for more in tomorrow's class and also next week's class. As I mentioned, next week, Wednesday class will be no class, but I will give you additional content. Maybe just a short video, maybe 40 to 60 minutes video with some exercise that you need to do. Okay, any question on this? Okay. So the way we see the substitutions, okay, first we need to identify correctly which part that needs to be substituted. You can try, well, at the first time, if you're not familiar enough, you could try like trial and error, which part is okay with the substitution, and some part maybe not can, well, not all integration can be solved through these techniques, but at least this one is the easiest to see, easiest to identify. Okay. Oh well, before this, let me write some conclusions first. Some conclusions. If u is g of x is a differentiable function whose range is an interval I and f is continuous on those intervals, then we could write that f of gx, g prime x, this is the chain rule forms when we derive, right? Dx is equal to this is what we did before. So the example is on the previous page. Then this is just a definition. Okay. And then if g prime is continuous on interval a to b, and f is continuous on range of u equal g of x, then integrations from a to b of f of gx, g prime x dx is equal to integrations f of u du, and with the endpoints g of a and g of b. Okay, now the second part here, when we take the substitutions, take a look at the a, b. It goes by, because we substitute with something that is the dummy is u, then all substituted here, because this is in terms of x, we are going to change this a and b with terms of u, in terms of du. So g of a and g of b. So it depends on. So basically, what we have in substitution is we are substituting the g with u. So this is going to be having some g. So as example, I think it's easy to see from the example. If we are having the, let's say, integrations from 1 to e
of ln x over x dx. I think it's obvious to see that when we have the ln x, if we derive it becomes 1 over x. And then we can switch the dx and du and becoming x du, and we can cancel the x. Right? So we could see that if letting the u equal ln x, this du over dx is become 1 over x. So dx will be x du, which canceling the x in the integration part. But then, don't forget that when we have u is ln x, then when x equal 1, okay, u is equal 0. When x is equal e, then u is equal ln e, which is 1. So these whole integrations will be integrations from 0 to 1. And this part here will be, let me write 1 over x, and then x, and then u, and then du. Okay, so we can cancel this part. So we have integrations from 0 to 1 of u du. Or we could write that this will be 1 over 2 u squared, and then substitute the 0 and 1. So half 1 minus 0, or this is going to be 1 over 2. Okay. But this is also a choice. Okay? If you want to keep 1 and e as it is, it's okay if you going to retake the u as x, if you going to rewrite u as x. For example, we integrate u become 1 over 2 u squared. So if you change u into x, then you need to also change this back to the original equation. For example, this is also equal when we take this half, and then this will be ln x squared, and this will be 1 and e. And it's also the same. This is 1, this is 0, and still the same 1 over 2. Okay. So you have a choice. You have a choice. You can try to change all into u, so x also changing to u, or at the end of this result, since you have the u result, you take that u and then change to x like this, and you can have these original equations as the original questions. Okay. Yeah, both are the same. Both are the same. Any questions so far? Oh yeah. How many of you are not or haven't learned integral from high school? I'd like to know how many. 3, 4. Okay, anyone? How about the Taiwanese one? I think a little half, right? High school integration, a little right. Okay, now the last part on this chapter 5 is about the symmetric functions. Okay, so let me put the definitions first, and let's discuss about this. Okay. So if you have a symmetric functions, if you have an even function, well, you could think the even functions like the polynomial, like x squared like that. Of course, if you are taking the from negative a to a, it means that you could take from 0 to a and multiply by 2. Okay? You could think like with visuals. Okay? Something like this. So if you take negative a to a, it seems that we have this half part, and then we multiply by 2 because it's the same area, right? The same area. So we could have this. Later I will prove later how to take this as a proof. But when we have an odd functions, maybe you could think x cubed. I think that would be easy to draw, right? So you have an odd function like this, like that. Okay? And if you remember what the under the x-axis means, it means a negative. So if you take the a here and negative a here, you see that these two curves is getting cancelled, right? Okay. So that's, I think visuals may be more probable for some of you. But let's say we are going to prove that in our mathematical forms. Let's do that. So first is taking this form here. To make it easy to follow, let's make 0 as our midpoint. So let's say we take negative a to 0. So we separate, becomes 2 integrations. And then the left part, the left integrations, I will switch the endpoints. Okay, I will switch the endpoints, becomes 0 and negative a. We can do that and add negative, right, as the property of integrations. And then let's say we have u is negative x. Okay, let u is negative x. We are going to prove this part when we put the negative x. So we can try to substitute with, let's take u as a negative x. So du dx or du is negative dx. And this part here, when x is negative a, u is a. And when x is a, u is negative a. Okay, the same. So then, this negative, this will be equal. So let's change all the f of x with f of u, or f negative u in our case. So we are going to change the negative a to u. So u is equal a, so it will be a. And du is negative dx, so negative f and negative u and a negative du, right? And then we can cancel this negative. So we will have integrations of 0 to a of f negative u du. Okay. So this will be this left integration here. Okay. So we can write completely that negative a to a of f of x dx, this will be equal to 0 to a of f negative u du plus 0, this is supposed to be 0 a f of x dx. Okay, and then we now implement the symmetrical theory. If we plug in negative u inside here, if it is going to be f of u, then it will be an even. If it is becoming negative, then it will be odd function. Right? And of course, if it is odd, then this part will be negative, plus the positive should be cancelled, so it should be 0. Okay? So if this is positive, then it will be twice of the value, right? Okay? So then we can write here the conclusions that if f is even, then f negative u is f of u, which means that the result is equal 0a f of u du Well, I hope you don't really get distracted by this axis u. It's the same thing. It's this variable, right? So it's this twice of that. So twice of the f of x dx. And then if f is odd, and this will be canceling, becomes 0. Okay, so this symmetry, this will be useful for at least the next chapter, is chapter 6, when we deal with the area between curves. So if you have like integrations that maybe starting from -2 to 2, and then if you take that integration, when you calculate without calculator, maybe you are having some mistake going on. I think it's better to get the 0 to 2
and then multiply by 2 if this is symmetric. It will be really helpful to avoid mistake. Okay, let me give you the last part is, I think, I will give you some examples. If you haven't done now, maybe we could have continue tomorrow. Okay, let me give you examples. So I will have two, each questions having two kind of integrations. It seems similar, but it's way different in results. So that's the first one. Okay. Now see the two. So we have four. We have four. I'm giving you like in two lines because you see the sine x over 1 plus cos sine x. The other part is similar, but it has squared in here. It has squared. So perhaps you could think which one of these two is the easiest one. And also the second line we have x and a square root of x squared minus 1. And this has the x square root of x minus 1. And all should be able to be solved by substitution. So you could try, maybe trial and error, okay, just to see how it forms, when you take the derivative, how it will be. And substitute it to the equations. And the idea is you are going to change the variable from x to u, or any variables you can think that what you want to substitute. It doesn't always to be u. You can take other variable as well, as long as it's substituted. Okay. So as long as you can change the x into the other variable, so you need to get rid of x. So first you need to think how to cancel the other part when you substitute. That's one thing that is important. I think the left part is supposed to be easier than the right one. Do you agree with me? Right? Right? So let me show you just one here for the left, the top left. I think you need to continue tomorrow. So let me just show you it in a quick way. So let u is 1 plus cosine x. So we will have du is negative sine x dx, right? So we could take this and then substitute the dx. So also I will change the, when x is 0, u is 2. When x is pi over 2, u is 1. So we have integrations from 2 to 1 of negative 1 over u.
du. So this will be negative ln u from 2 to 1, so negative ln 1 minus ln 2. So this is 0, and this will be ln 2. Okay. That's the first one, and the rest will be tomorrow class. Okay. Okay, because we don't have much time left, so I will go to the feedback slide. We can discuss more about this for tomorrow, okay? And then maybe adding a few more examples also. So tomorrow is expected to have some review, some examples, and moving to the new chapter 6. Okay. I hope you still remember the introduction part of integral, the summations and so on and so forth. Okay, I think everyone ready? Okay. Okay, let's start. Start the countdown. Okay. Okay, maybe you need to look on your phone screen. It's from -2 to 4. Okay. So maybe -2 is here. 4 is around 2 to 4 here. So you will have from here going here. So what you need to do is you need to take rectangles, okay, from this -2. Take to the right endpoints. Okay. Take to the right endpoints like this, and you have the 6 subintervals. So you could take the b minus a divided by 6, which is 1. Okay, if you knew already, the delta x is 1. So you need to find the rectangle. So the one here is positive, the one here is negative. Right? Yeah, you need just to really careful to see which one is the points and compute the rectangles, okay, and using the right hand points. And I think because the delta x is just 1, all the numbers will be just not really in decimals, I think. If it is decimal, it's a simple decimal. So we'll see from here, this one rectangle here. And from this -1 to 0 is no rectangle. And then the other part is going to be going down. So we will have from 0 to 1 is going here. Maybe taking some points there. And from, oh, 1 is here. Oh, it's from here, sorry.
Oh.
From here.
What?
So 0, 1, 0, 1, 2, 3, 4 is in the middle. in the endpoints there.
Oh.
Sorry. But I think if the time is longer, I think it should be easy to compute. You ready to compute?
Yeah.
Okay. Sorry. It's supposed to be going here. And the part here is there will be some half here and half here. Yeah, and not a comfortable question, but it's supposed to be easy questions. And did the TA really move to the chapter 5? Last time. No, I really was.
Third questions at the meeting. The first two questions. Oh yeah,
Yeah, it's a zero. Yeah, with some approximations, when you use the right endpoints, it will be zero.
Okay, I got it correct.
Okay.
Even though I calculated the rank wrong.
Okay. Who is Broom? Who is Broom? No. Okay. Okay, let's take the last question. I also forgot the question. Yeah. There is no picture.
Yeah.
Why? I think I missed out the.
No.
Yeah, just cancel the question. Yeah, just cancel the question.
It's impossible to guess.
Yeah,
It's impossible.
yeah, it's most impossible. Yeah, let's just skip that.
Okay, it's impossible to, but you can still.
Yes, but we don't really have the picture. Okay. I would like to know how is your feedbacks on our midterm. But I saw in the 15-30 minutes, the first 30 minutes in the classroom, and saw some answer from you. I think you guys get correct answer. But at least like a few questions. But I'm not sure the other one. I'm not sure the other one.
I think the midterm and next year midterm is way much easier.
Way much easier.
Yeah.
And increase some parts. Yeah, some part. But I also make sure that I give you the question that you need to be able to solve. You should be able to solve. Yeah, this can be my consideration for my final exam. I'm thinking to give you a chance using A4 notes to prepare some notes. Yeah, I think that will be helpful. But if I've given you the notes, then the question will be difficult. Yeah. That's a compensation. But if not notes, then it's supposed to be can be solved. Yeah, doable. Okay. The last question is the just attendance.
Zero, zero. Yeah. I guess I and Mexicans were going with a school food all time. And we won for free. I feel extremely sore,